Now we start explaining the design of encoders. X, Y, and Z to be straightforward. So if we look at X is equal to 1 when the following: D4 is equal to 1, or D5 is equal to 1, or D6, or D7. Same thing for Y. Y is equal to 1 when D2, or D3, or D6, or D7, and Z is equal to 1 for D1, or D3, or D5, or D7. And from these observations, we can immediately functions for X, Y, and Z. And with the Boolean functions, the hardware implementation becomes straightforward, where we need only 3 OR gates to develop the outputs X, Y, and Z, as we can see in this diagram here. Therefore, the 8 to 3 binary decoder is straightforward. It has these 8 inputs and these 3 outputs, as we have just explained. Of course, at any one time, as we mentioned, we again stress the fact that only one input line has a value of 1. Only one input line and exactly one input line. Therefore, there has to be one input line that is equal to 1 and only one input line. We have mentioned this in order to move forward with what we call priority encoder. Now, the priority encoder, it is like an encoder that we have just described. However, it has another function, additional functionality, which is it is possible for multiple inputs to be 1, but in this case, we give priority to one of the bits only. So we can have 2 inputs 1 or 3 inputs 1 and so on, but only one of them will have priority. We give an example of 4 to 2 priority encoder with the priority given to 1 bit. Because the question will be, to which bit do we give the priority? Which bit has the highest priority? If we assume that D3 has the highest priority, the truth table will be developed as follows. Now, if we assume, of course, we assume that more than one input can be 1, but also we assume that it is possible that no inputs will be 1, which means the inputs D0, D1, D2, D3 can take the values 0, 0, 0, 0. And if that is the case, we say that the input is not valid. So we have 2 data inputs, X and Y, 4 data inputs, D0, D1, D2, D3, and 2 data outputs, which are X and Y, which will be the code of the input, and we will have an additional output now, which we call a validity bit. This additional output to indicate whether the input is valid or not valid. So if all the inputs are zeros, as we can see in this row here, we say that the output is not valid. So validity is 0. However, if the inputs, if D0 is 1 and D1, D2, D3 are zeros, X and Y will be zeros, and this output is valid because we have one input is 1, so the output is valid here. But when we have D1 is 1, we don't care about the value of D0 because D1 has a priority over D0, and the output will be 0, 1, and it is valid output, of course. And if we have D2 is 1, we don't care for the inputs D0 and D1, and the output will be 1, 0, which means D2 is 1. And finally, when D3 is 1, here, we don't care for the values of D0, D1, and D2, and the outputs will be 1, 1, indicating that this input is a 3, as we see here, and it is a valid output. So let me repeat, just to make sure it's clear. When the priority is given to D3, as we have mentioned here, then we look again at the table. When D3 is 1, we don't care about the values of D0, D1, and D2, and the outputs will be 1, 1. But if D3 is 0, we look at D2. If D2 is 1, we don't care about the values of D1 and D0, and the output will be 2, and so forth. Of course, we explain this in order to derive the Boolean functions for x, y, and v given this table here on the left-hand side. Now, to develop that, actually, we know that D0, D1, D2, D3 have 16 different combinations. So if we want to develop the table for x1, let us do it here in this space. As a matter of fact, we can write here a kernel map of 16 different cells as follows. So we have here D0 and D1 on the left-hand side, and we have D2 and D3 up, and these will take 0, 0, 0, 1, 1, 1, and 1, 0. Same thing here, 0, 0, 0, 1, 1, 1, and 1, 0. Let us start with this row here. When D3 is equal to 1, let us do the kernel map for x first. X is equal to 1 when D3 is equal to 1, irrespective of the values of D0, D1, and D2. So on the kernel map, this row here, the last row, corresponds actually to 8 different cells, which is when D3 is 1. Therefore, D3 is 1 here. So we have, this is 1, 1, 1, 1, 1, 1, 1, 1. So all these 8 cells corresponds to D3 is equal to 1. Now we move on to this. X is 1 in this row here. And this row has D2 is 1 and D3 is 0. We don't care about D0 and D1. And this, therefore, this row here corresponds to 4 cells on the kernel map, which is this column that has D2, D3, 1, 0. So this is 1, this is 1, this is 1, and this is 1. And of course, the other 4 cells remain in the map. Their values will be as follows. For the cell which is D1 is 1 and D0 don't care, and D2, D3 0, 0, which is D1 is 1 is the second and third rows, and D0 don't care. Therefore, this will be 0 and this will be 0 here. Finally, the min term 1, 0, 0, 0, which is this row here, which is min term 8, this is also 0, and 0, 0, 0, 0, this will be don't care. So this is the kernel map for the variable x, and exactly in a similar way, we develop the kernel map for y, which also we do here to make sure that we understand thoroughly this problem. So that is the kernel map again for y, and 0, 0, 0, 1, 1, 1, and 1, 0. This is D0, D1, and 0, 0, 0, 1, 1, 1, 1, 0 for D2 and D3. And y will be equal to 1 here in the last row, which are these 8 cells, 1, 1, 1, 1, 1, 1. And it will be equal to 1 in this row, which is D2, D3, 0, 0, and D1, 1, and D0, x, which means 0, 1, and 1, 1. So 0, 1 is 4, and 1, 1 is 12. So these, and otherwise, y will be 0 for here in this row. So these are zeros, and it will be 0 in this cell here also, and this will be don't care. And from these kernel maps, we can find out the expressions for x and y. X will be this loop and this loop. That's easy. So x will be D3 or D2, and y will be this loop here and this loop here, which means y will be D3, or this loop here is D1 and D2 prime, D1, D2 prime. And we are done. With these now, we can really, so that is X, and I believe there is a mistake here in the kernel map. These must be zeros as we have just derived them on the other slide there. And with this now, we have the Boolean equations. We can easily draw the logic diagram because X needs just an OR gate. That's X, D2 and D3, and Y needs an OR gate where we enter D3 and D1, D2 prime come from an AND gate, and then this is Y. And this is the complete circuit for priority encoder that we have just explained. Of course, V, if we look back at the truth table that we developed at the beginning, V will be 1 when any of the input D0 or D1 or D2 or D3 is 1. Therefore, all it takes is just an OR gate inputting all these variables as that we can see here. And this concludes our discussion to the priority encoder.